Hi everybody, this is chapter 11 and it's basically going to be, the topic is describing chemical reactions. What we're going to do here is we're going to talk about how to balance chemical equations is basically what's happening in this section. Okay, here we have one of these newfangled cars that has a fuel cell in it, okay, and it's an electric car, but it doesn't get plugged in. It actually uses what's called a fuel cell. And a fuel cell uses a chemical reaction without the typical combustion you have of a gas engine. Okay? You are having a chemical reaction though, and we'll talk about that later in this presentation. Okay, the first thing we're going to talk about is something called a skeleton equation. Okay, you know what a skeleton is. It's inside of you. It holds you together. Okay? So it's the basic part. I don't think people would really be able to tell the difference between each of us as easily if we just walked around as skeletons. So it's important that it's there because it supports the whole structure, but it's not the whole story, but it's a start. Okay. Your body is a big chemical factory. There's all sorts of things that are happening right now as you're listening to this video inside you. One of the biggest and most important things is the creation of energy for your body from the food you eat. So you digest your food. That's a chemical reaction. Then after you digest it, it gets simpler and simpler so that it can provide the energy that your body needs to go through all its processes. Plants, on the other hand, make food. Okay? So the process of turning sunlight into energy for the plant, or food for the energy, food for the plant, is called photosynthesis, which you've learned in biology before. Chemical reactions require that a change is made in the substances. In other words, whatever substance you start with, you end up with a different substance. So, at least one thing is changing, if not everything, in a chemical reaction when you make new products. Cooking is always a chemical reaction. If you think of using a recipe, you have certain amounts of ingredients that you mix together and you create the food that you want. Chemical reactions are like that. You start with ingredients, which we call reactants. Okay, so the ingredients of a chemical reaction is called, let me go back, and I want to go to my pen because I want to change my color to red because I like red. Okay, so our ingredients are called reactants. Okay, so we're not going to use the word ingredients anymore, we're going to use the word reactants. That's the chemical word. And we basically, in a recipe, we would heat them together in an oven to make, for instance, a cake. A lot of times we heat chemicals together to make something new. All right, in this picture, I guess they were going to make muffins. So why do we use chemical equations? I'm always saying chemists like to use less ink. Okay? Well, as you can see, this nice paragraph, anytime we write things, we write a lot of things down. Chemists like to use less ink, so they basically make things into a shorthand. Okay, so a chemical equation is a shorthand notation to tell us what is happening and at the same time conveying lots of information about the reaction. So we're going to talk about the first simplification of what we're doing in a chemical reaction by making a word equation. So we take a description and simplify it into the most simple amount of words we can have to explain what's happening. Okay, for any chemical reaction, we always have something on the left-hand side, which we call the reactants. Remember I said they were the ingredients. And then we produce products. So that's kind of like what it is that we're making. And this here is an arrow that joins the two together. So we're going from this to this. We follow the arrow to our products. So reactants are always on the left and products are always on the right. We see the arrow that separates them. So how do we say that? Instead of reactants give products, we use the word yields. Sometimes we might use gives. Sometimes we say certain things react to produce, okay? But these are words that we will use in saying reactants yield. That's really what the arrow means, yields, okay? All right, let's look and see how a word equation is made. Okay, so here we have an old jalopy of a truck. So you could write out the sentence, iron reacts with oxygen to produce iron 3 oxide, or rust. Okay, so that's what rust is. It's easier to just put this in a word equation. So we have iron, okay, and we have oxygen. And we're adding them together, so we put a plus sign. So we can say iron and oxygen, or we can say iron reacts with oxygen. So this plus sign means this whole part of the sentence up here, reacts with. Okay, here's our yield arrow. So that's the to produce part. Okay. Then we have iron 3 oxide. We don't need to write rust. That's just so we know that in the sentence that iron 3 oxide is rust. So these two things together give us this new compound. And that's just all words. That's the name that we learned by using Roman numerals. So we're all set. Okay. So we wrote the names on the left-hand side of the equation. And we wrote the products on the right-hand side. The reactants were separated with a plus, as I said. If we had more products, we would have a plus over here too. Okay, and then we have the yield arrow showing the direction of the reaction. Okay. All right, here's something that you've probably used before. We've got some hydrogen peroxide somebody put on their cut, and it's bubbling. So sometimes, if a chemical reaction has occurred, we will notice something. So in this case, for this reaction, we noticed that gas was generated. So these bubbles are gas. So we know that some gas was made from this liquid, hydrogen peroxide. So we have at least gas as one thing. So two new substances are produced in the reaction, oxygen gas and liquid water. Okay? So hydrogen peroxide decomposes to form water and oxygen gas. So here's our word equation. Hydrogen peroxide, that's the stuff in the brown bottle, will make water and oxygen. So this is oxygen. So the oxygen is what's helping get rid of the bacteria for you. Okay, another important equation, if you have a gas stove at home, you may be using methane. You could be using also propane, but we're going to look at methane because methane is the simplest of the gases that we use for cooking. Okay, when you burn something, you need oxygen. At least here on Earth we do. I think that's true almost any place. So if we're going to burn methane, we're going to add oxygen to methane and light it. Okay, because to keep a flame going, we need oxygen. And when we do that, we get carbon dioxide and water. Okay, So methane plus oxygen gives us carbon dioxide and water. So that is a word equation where we have two reactants and two products are produced, and we see the direction of the reaction. Okay, well, that tells us some information. That gives us a general idea of what's happening. But a chemical formula, the things that we learned about in the last chapter, or in 2 chapters ago actually, is a way of even using less ink, number one, but it also tells us more about quantities or how the reactants and products, how many elements are in each of them. So by using things like these subscripts here, right here, we know that O2 doesn't exist as one oxygen, it has two because it's a diatomic molecule. Iron can be alone. And then when we make our iron 3 oxide, we see that we have these subscripts for the formula. So we have more information about how the chemicals or the reactants and products are starting out and making. Okay? So here's our reactant formulas, and this is our product formula in this case. Okay, so this here is called a skeleton equation. The reason it's called the skeleton equation, it's one step up from our word equation. Okay, it's basically taking iron. Okay, let's write this as a word equation. Okay, iron plus oxygen produces iron 3 oxide. So what we did is we took iron and basically turned it into its symbol, oxygen, diatomic, okay, Fe2O3, iron 3 oxide. So we basically were able to change our word equation into the formulas. Okay, so this is not the full story yet. Okay, we've actually just said the same thing we said in our word equation, but transcribe that into the formulas. Okay, but we're not done yet because remember the good old law of conservation of mass. If we look at this skeleton equation, we see one iron here, but we see two irons here, we see two oxygens here, but we see three here. So where did these extra irons and oxygens come from? This equation is not telling us that. I thought equation means equal, right? So there has to be something more because the skeleton equation is not telling us. It does not indicate relative amounts of reactants and products. Okay? It's just telling us, it's basically taking the word equation and putting it in the formula. Okay? And that's what we just did. Okay, so let's go and get some more information. Next thing is, what form of matter are all of these substances? Well, iron is at room temperature a solid. So we're going to use a S in parentheses next to the formula to tell us that iron isn't solid. At room temperature, oxygen we know is a gas, so we use G in parentheses to tell us that. Rust we know is a solid, so we're going to do that. So these they're really little small letters in parentheses after the formula. So what are the letters we can use? We can use solid, S, L for liquid, G for gas, and AQ for aqueous. What does that mean? It means something's dissolved in water. It's a solution. Okay? So this is still a skeleton equation with a little bit more information, but it still isn't following the law of conservation of mass. Okay, let's look at something else. Okay, sometimes we have a reaction that requires something else to work, okay, but it doesn't participate in the reaction. So it usually does this, a catalyst, something called a catalyst. Catalyst means something gets it started. And a lot of times what this means is it also speeds it up, because the reaction could occur, but it might take a really long time for it to really happen. So we might add something to it, but this catalyst here is manganese oxide. By writing it on top of the yield arrow, we're saying it's in the bucket, but it's not participating in the reaction. So if you put 2 grams of this here, you can get 2 grams of this later on. All right, so what's a catalyst? A catalyst is a substance that speeds up a reaction, but is not used up. Okay? It's not a reactant and it's not a product. That's why we write it here. Okay, I would take a screenshot of this page because these are the symbols you might see in chemical reactions. Plus, okay, separates either 2 reactants or 2 products, or even if you have more than 2 products, sometimes you have 3 products. Separates the formulas in a chemical reaction. An arrow with one direction means yields. Sometimes we use 2 half arrows in both directions. This means that the reaction can occur going forward, and the reactants can become, the products can become reactants and go back and form more reactants. This is a reversible reaction, which we'll talk about later in the course. We also learned the 3 states of matter have little parentheses with S, L, and G after the chemical formula. We also have, we also have AQ, meaning that the chemical that we have is dissolved in water. Okay. Oh, this one here, either one of these, this little triangle or the word heat means that we're heating up the reactants so that they form the products. And if we have some chemical or element like platinum here on top of the arrow, it means that a catalyst has been added to speed up the reaction or to help it to occur. Okay? So please take a screenshot of those, know what they mean, and use them when you balance equations. All right, let's do some practice. Okay? Hydrochloric acid reacts with solid sodium hydrogen carbonate. The products formed are aqueous sodium chloride, water, and carbon dioxide gas. We're going to write the skeleton equation for this chemical reaction. Before we do that, let's write a quick word equation. So we have hydrochloric acid reacts, so that's plus. Okay. Hydrochloric acid will be, well, it could be liquid, but it's probably aqueous. Okay, so I'm going to put aqueous there. Solid sodium hydroxide. Oh, sodium hydrogen carbonate. So this is baking soda. Okay. And this is solid. Okay. Products formed are aqueous sodium chloride. Oh, you know what I'm doing? I'm writing the skeleton equation. I should write it out. Okay. So I should have said sodium hydrogen and I could have put, after that I could say solid. And then I get sodium chloride. And that is in solution plus water plus carbon dioxide. I'm running out of space. And you can see why this is not practical. That's a gas. Okay, so, and you see why I started writing the skeleton equation right away. All right, so how are we going to translate that into formulas? So we write the correct formula for each substance in the reaction. We're going to indicate the state of each substance. We're going to put the arrows in the correct place. We're going to put plus signs between the reactants and between the three products. So there's our reactants, sodium hydrogen carbonate, hydrochloric acid. Then we got sodium chloride, water, and carbon dioxide. That's kind of what I did with the word equation. Okay, now we change those into the reactants. Sodium bicarbonate, solid. HCl, aqueous. Product, sodium chloride, aqueous. Water, liquid. CO2 gas. Okay, now we're ready to put them into equation form. So all we do is we take the formulas we just saw on the last page, put a plus sign between them for reactants, arrow, separate reactants from products, and then copy down from that list. Okay? So that's all that's to it. So you can write it out as a word equation, which, as you can see, that gets kind of wordy, but you could also just put it in a list if you wanted to do it that way. Okay? Once you know what the formulas are, you can just look at the question and go right to the skeleton equation too. Okay. What's some advantages of using an equation? Okay, we kind of talked about it. I'm not going to put this on play pause it, but let's think about that for a second. Okay, chemical equation for a reaction is much easier to read. Okay, it shows all the relevant information. It shows you what formulas you have, so it gives you an idea of what you have to get to mix together. It shows you what state of matter it is. It tells you if there's any catalyst or if you have to heat things. It's just easier to read than a lot of words or a lot of sentences. All right. What are the steps for writing and balancing chemical equations? So now we're going to go from our skeleton equation to a fully balanced equation, which takes into place the law of conservation of mass. Okay, the law of conservation of mass. We have to have exactly the same number of atoms on the left-hand side of the equation as we do on the right-hand side of the equation. And we can show this by balancing our equation. Okay, let's take this from something that's not chemicals now, but say you are a bicycle manufacturer. For instance, a lot of times people will say, why do I need to know this? Okay, there are going to be times in your life, in your job, where you're going to have to decide how many things do you need to make something maybe. It might not be a bicycle, it might be something else. So learning a chemical equation helps you understand in your mind how things are related to other things. Okay, so what do you need to make a bicycle? Okay, you need a frame, you need some wheels, you need a handlebar, you need pedals, and then you get a bicycle. Okay, so the reactants that we need are frames, wheel, handlebar, and pedal. Okay, now, how many frames do we need? Well, you only need one frame for a bicycle. How many wheels do you need? Well, you need two. How many handlebars do you need? Well, 1. And pedals, you need 2, right? So now we have to decide how many we need. Okay? So that word equation, you would get like not a full bicycle because you don't have any quantities there. So you need to find a way to put quantities in. All right. So let's look at this. We're going to call frames F, wheels W, handlebars H, and pedals P. Okay? So if we look at our bicycle, a bicycle here, okay, has 2 wheels, 1 frame, 1 handlebar, and 2 pedals. Okay? They didn't say anything about seats, okay, but okay, we're counting the seats, so I guess it's part of the frame. So we said we had frame, 1 wheel, 1 handlebar, 1 pedal. No, that's not right. We need 2 wheels, right? So we're going to need 2 wheels. And we're going to need 2 pedals. Okay, one over there and 1 over there. Okay? So, there we go. So we need 1 frame, 2 wheels, 1 handlebar, and 2 pedals. Notice we don't put anything in front of the frame and the handlebar. So if you have 1, you don't need it. Remember we did that when we had things like H2O. The oxygen doesn't get a 1. When you did your crosses, if you made formulas, you got rid of that 1. So we don't put 1s. Again, we don't like to use extra ink. Okay? Okay, so what do we call these? We call them coefficients. Just like, I think you do that in Algebra 2. Like 2x, 3x. They're coefficients. Okay, they're small whole numbers that multiply. Okay, whatever this is. So 2 times W, there's 2 wheels. There's 2 pedals. Okay? They help us balance the equation. Okay? So there is a statement that basically agrees with the law of conservation of mass. So if you look right here, there it is. Mass is conserved. Okay? So a balanced chemical equation, each side of the equation has the same number of atoms of each element, and mass is conserved. That's what must occur in a reaction. Okay, what happens, okay, in a chemical reactions? In a chemical reaction, the bonds holding the atoms together are broken. Okay, and then we have new bonds formed, okay, in our products. The atoms don't change. They're just rearranged. Mass is always conserved. Okay, very important concepts. Okay, reactants bonds are broken, products new bonds are formed, the atoms are the same on both sides. I should say the elements are the same on both sides. They're simply rearranged. Okay? They're different substances. Remember, hydrogen gas is a gas at room temperature. It's explosive. If it's reacted with oxygen, it forms water. Water's a liquid at room temperature. It is not explosive. Okay? Different properties, different substances. Okay? All right. Here is a summary of what you need to write a balanced chemical equation. Number 1, write the skeleton equation. Put things in their formulas. Then you're going to use coefficients to balance the equation so it obeys the law of conservation of mass. You must have the same number of atoms on both sides. All right, here's a reaction of carbon with oxygen. So we're basically burning carbon to form carbon dioxide. So we start out with one carbon, oxygen is diatomic, we get carbon dioxide. Okay, so everything is balanced because we've got one carbon on this side, we've got two oxygens on this side, two oxygens on this side. You don't have to change everything. This is balanced. Okay, now this one is a little bit different. Hydrogen and oxygen are both diatomic gases. Okay, but water only has one oxygen and two hydrogens. So the hydrogens are okay, but the oxygen, this one has one more oxygen, so we have to take that into consideration. We need two oxygens on this side, so we would put 2 in front of the water. Okay, so we would have 2 waters, but now our oxygens are okay, but we only have 2 hydrogens. Okay, so we need 2 more. So now we're going to have to get 2 more hydrogens. So now we have 2 hydrogens. Let me get the pen. 2 hydrogens. 1, 2. 1 O2 and 2 waters. So 1, 2, 3, 4. 1, 2, 3, 4. So we have 4 atoms of hydrogen. 1, 2 oxygens. 1, 2 oxygens. Now it's balanced. Okay, we talked about the fuel cells in a car earlier. Now, what that is, it's basically hydrogen and oxygen are combusted, basically. Okay, but what is it that you make? Let's go back. Water. Water is basically not pollution. So therefore, no bad carbon dioxide, no bad nitrites. All those things that form pollution, it's just extra water vapor. So it might rain a little bit, who knows? Okay, so that's a zero emission car. All right, I'm gonna go through this. I'm gonna let this on the screen for a second. Take a screenshot. This is the rules 1 through 6 on balancing equation. Okay, very simply, change the words to correct formulas. Write your skeleton equations. Then start deciding how many of each of the atoms you need on each side. Use coefficients to make that happen. Okay, then go back and check to make sure when you've done it that everyone is accounted for. And finally, one of the things, number 6 is really important. As you do this, you may have made too big of numbers. So make sure that when you look at all the coefficients, it's the smallest ratio. For instance, if you had an equation like this, where these are your coefficients. You might realize, now this isn't always the case, it might be better to have let me see, I said 4. So I said 4, 2, 6, and 8. That's really probably not the best way, but instead of 4, 2, 6, and 8, you might end up having, better to say 2, 1, 3, 4. It could probably be reduced to that as the coefficients. You would have to check it out. Okay? All right, now we're going to have a real case scenario. Okay, we had some copper wire, and we put it in a solution of silver nitrate. After a period of time, the copper gets coated with silver, the wire. All right, so what happened? Well, where did the silver come from? The only place the silver could have come from is from the silver nitrate. So this is the formula for silver nitrate. They said it was a solution, so that's aqueous. Copper was a wire, so we know it's a solid. So these are our two reactants. Okay, so for the silver to leave the nitrate, it has to displace some copper. Okay, so we must be forming copper nitrate. All right. Okay, so they're saying that the copper reacted with the silver nitrate, so we must form this as an aqueous solution, and then we know we get silver. So in other words, what we know is we start with this and this, and we know we're making this, so the only thing that we have to kind of decide is what does the copper make, and that's what we do there. So now this is our skeleton equation. We have all our formulas, all right, but we don't know, what has happened there. This is kind of interesting because, well, copper we know could be copper nitrate, copper 1 nitrate, or copper 2. This looks like copper 2 nitrate. All right. Now, since nitrate is on both sides and it's not breaking down into nitrogen and oxygen, it can be used like any ion. So we're just going to treat it like an element. So first thing we're going to say is, look at the nitrate. There's only 1 nitrate in silver nitrate, but there's 2 in copper nitrate. So we have to take care of that. So we're going to put a coefficient 2 in front of the silver nitrate, because we can't put it in the middle. We have to put it for the whole compound. All right? So when we do that, that means we have 2 silver on this side, so we're going to have to also worry about this silver. Okay? So then we're going to put a 2 over here, so our silvers and our nitrates are balanced now. Now we have to look at copper. We have 1 copper, 1 copper. That looks fine. All right? So that's balanced. All right, let's look at another case. Okay, aluminum is something that forms a what we call a patina. It's similar to what happens to the Statue of Liberty. If you know copper is brown, the Statue of Liberty is copper, and it's green. Okay, anytime you see green roofs that are copper, what happens is when copper is out in the elements, it actually forms an oxide, and it's a green color. This protects the underlying copper from corrosion. The same thing with aluminum. When it forms a kind of a whitish aluminum oxide, it is also protecting the aluminum from further oxidation or rusting. So here is our equation. This is our skeleton equation. We have aluminum solid, oxygen, that should be a gas. Okay, so somebody who typed this did not do it right because oxygen is not a solid. Okay, so this should be a gas. Let me write G. Okay, and aluminum oxide is a solid. Okay, as we can see, we have 1 aluminum here, we have 2 aluminums there, 2 oxygens, and 3 oxygens, so it's not balanced. All right, so what do we have to do next? Okay, the first thing, I usually start out with the first thing, aluminums. Okay, we need 2 over there, so we put a 2 in front of Al. Now go to the oxygens. We have 2 and 3. Well, that doesn't go in that easily, so we need the least common multiple. What's the least common multiple of 2, 3? That's 6. So that means we're going to probably have to put a 3 in front of O2 and a 2 in front of Al2O3. Okay? So now we have 6 oxygens, okay? And I say we're going to have to take care of the other oxygen. We're going to have to put a 3 there, right? So our oxygens are fine. But what do we do to our aluminum? Now we've got 4 aluminums on the right. Okay, we have 4 here. There's 4 aluminums. And there's only 2 here. So that means we have to multiply this by 2. So that becomes 4. Now it's balanced. Okay. I'm going to have you do this one and play pause it. All right, so try this one and play pause it. It's a little trickier, okay? Because I'll give you a hint. With the oxygens, wait to the end to balance the oxygens. So in other words, balance your carbon and hydrogen first, then balance your oxygens, because you have oxygens in 2 places on the right-hand side. That's my hint. Okay, go for it. All right, so what do? So we look at this, and the first thing we're going to do is we're going to say, let's get the carbons done. So I have 3 carbons. Good. Next, I'm going to look at my 8s, hydrogens. So I have 8 there, so I put a 4 here. So 3 times 2 is 6, and we get 4 here. So the total number of oxygens on this side are 10. So we're able to do 5 there. All right? That's how we go about that one. All right, here's a summary of what we learned in this section. You might want to take these down as notes. Definitions that you should know. Again, if you want to screenshot that or take that as notes. Some more definitions that you should know. And the big idea, reactions. The law of conservation of mass states that mass is neither created nor destroyed. Most important idea for balancing equation. In order to show that a mass is conserved during a reaction, a chemical equation must be balanced. Okay, that's it. See you next time.